Alright, so now I want to talk about telescoping series. A telescoping series is a series of the form where the sum is n equals 1 to infinity of an minus an plus 1. And we have a theorem here that allows us to evaluate the limit of a telescoping series. Observe that basically what we have here is that the limit of a telescoping series, we use the first term and the last term. So we get that it's a1 minus am plus 1. I should note that problem 2 was an example of a telescoping series. Notice that the 1 minus the 1 over n plus 1 for our answer came from this theorem here. To give you an idea about why this theorem is true, we can look at the sequence of partial sums of a telescoping series. So if we look at the mth term in the sequence S of m, remember this is the sum of the first m terms. So what we get here is that our first term is a1 minus a2, second term is a2 minus a3, third term is a3 minus a4, fourth term is a4 minus a5, and this continues up to the last term here is am minus am plus 1. Notice that when we're taking the sum of this, there are a lot of terms that can cancel out. So we see this minus a2 will cancel out with this plus a2. And the minus a3 will cancel out with the plus a3. And the minus a4 will cancel out with the plus a4. And this actually continues. And notice that the only terms we have left are the first term and the last term. And so this gives us that this sum is actually equal to a1 minus am plus 1. Hence, if we're taking the sum, I'm looking at the limit as m goes to infinity, of the sequence of partial sums. This is limit as m goes to infinity of a1 minus am plus 1, which is exactly the statement of the theorem. All right, so now I want to talk about a couple of properties that we can use when trying to figure out the sum of an infinite series. So the first one here is the test for divergence. The test for divergence simply says if the series converges, then the limit of its sequence must approach 0. The second part of this theorem is related. What this says if the sequence does not approach 0, or the sequence does not exist, then the series actually must diverge. It's important to note here that if the sequence approaches 0, we don't actually know if the series converges or diverges. The statement of the divergence test only tells us that when the series converges, then the limit is 0. All right, so something else that comes up is if we have two series that eventually become the same. So it could be that the first so many terms don't agree, but after that, there's some point where after the number n, all of the terms are actually equal to each other. So it turns out that's essentially the same series. If one of them converges, the other one must converge also. If one of them diverges, the other one must diverge also. All right, so now I want to talk about a couple of properties of convergent series. So if we have a convergent series A of n that converges to some number A, and a convergent series B of n that converges to some number B, then we can look at the sum of the A of n plus B of n. That series is actually just the sum of A of n plus the sum of the B of n, or A plus B. Likewise, the minus, this would be equal to A minus B. And so we can see that this is equal to A plus or minus B. I should note that if we're talking about addition or subtraction of a divergent series where one of them also converges, so if A of n converges and B of n diverges, then if we look at A of n plus B of n and A of n minus B of n, both of those series will diverge also. And another property that we have here, looking at property 2, if C is some number, if we multiply a series by a constant multiple, its sum is just multiplied by that constant multiple C also.